All right, so the plan today is to finish up one last problem in geometry applications and then talk about uniform motion applications. I think um, these uniform motion applications are a little more straightforward maybe than the geometry ones because we're kind of just always using distance equals rate times time in one way or another. So um, so I think 3.5 will be you know a section that's not maybe as difficult as some of the other ones. Also, the nice thing about 3.5 is that with context, again, we have units and things like that. We have a little more context than in our geometry application. So a little more ways to check our work or to get an idea or a hint of what the right approach is. Okay, so the quote of the day is that velocity is a vector quantity consisting of both speed and direction. So this is something that one of my wife's coworkers from a few years ago liked to say. And basically her point was, if you want to get something done, you have to point yourself in the right direction and start going, right? If you have a lot of speed where you're running in circles, you don't have very good direction. You're putting in a lot of effort, but you're just kind of spinning your wheels. If you point yourself in the right direction, but then just sit there, you also don't get anything done. So I think that was a kind of an interesting idea. Or the way that I would say it is something like effectiveness equals efficiency times effort. So if I spend a lot of time figuring out, say, the most efficient way to learn some material, and this is a tendency that I have. So if you make a study plan and you spend 6 hours making your study plan for an exam, but you never actually sit down and study, then that's not very helpful. But also, if you just sit down and study completely randomly, well, you could probably make a lot better use of that time with a little bit of planning. So, kind of balancing planning and doing is the way to get maximal effectiveness. And then at some point, you graduate, you have to go out and get a job. You want to get promotions in that job, and so on. And to perform well in a job, you need to be effective, but also the things that you're effective at need to be relevant to the job. So it's kind of a buzzword today, but you want to have an outsized impact to your company. And I think of impact as being effectiveness, so actually getting something done times relevance. So does your company actually care that you get that done, right? If you put in all of the efficiency and effort to be the best wiffle ball juggler in the world, that's probably not too economically useful, right? It's a really cool skill, but your company might not care so much about that. So what is the impact that you're having on the company? And that's directly related to the relevance to their mission, to their purpose in the economy. Okay, so moving on to solving geometry applications, the last problem. We talked quite a bit about geometry applications last time. And here we have an application problem. So this is less of a problem like, here's a triangle, find the third side or something like that. This is more of an application, but maybe we can extract some geometry out of this and then turn it into one of those problems from last time. So here we have a 10-foot string of lights attached to the top of an 8-foot pole. How many feet from the base of the pole should the end of the string of lights be anchored? So let's draw a little diagram. We have our pole here. We have a 10-foot string of lights attached to the top of an 8-foot pole. So this is 8 feet tall. How many feet from the base of the pole should the end of the string of lights be anchored? One little pet peeve of mine is I like problems to be well posed. So to be very explicit about exactly everything that they're asking. Um, it's, I suppose, an implicit assumption here that we want the string of lights to be straight. So we don't want them to be all droopy. So I have a string of lights. I'm going to anchor it to the ground. So this is the string of lights. It is 10 feet long. And then this is the ground. And this is what I don't know. How far away from the base of the pole do I want to anchor the lights so that they're stretched taut? But now nicely, I see that this is, again, presumably a right triangle. We're, I suppose, presuming that the pole is perpendicular to the ground, is 90 degrees, makes a 90-degree angle with the ground. So again, some implicit assumptions here. So we're assuming a 90-degree angle here. We are assuming that we want the light stretched taut. And we can go on from here and solve our problem. As kind of a side note, like I said, I like when everything is stated explicitly, but really, it's actually a very important, an important skill to have in general, but also in math, is to figure out what are the implicit assumptions or what are reasonable implicit assumptions. We naturally do this all the time. Anytime that we're talking with one another just about anything, there are all kinds of implicit assumptions that we have, that we make during such a conversation. So, when your boss tells you, hey, I want you to do this thing, they're probably not going to spell out for you every detail of how they want you to do that. It's kind of on you to think about, okay, what are the constraints? What are the goals of my company, of my boss, right? And of the job, what are the practical constraints? How do I work around those? So, for instance, we know that we want to solve this problem. We have, an 8-foot tall pole. Well, if the pole was slanted at some angle and the lights could be droopy, and right, how am I ever going to solve this? I know that I need to overlay a couple of assumptions to make this into the type of problem that I know how to solve. And that's also a skill in math, particularly slightly more advanced math, where you say, okay, I have some structure that I'm working with, and I maybe want to prove a theorem. I want to make a claim on the basis of that structure, but maybe I don't quite have enough to prove that theorem that I want to prove. Is there one more assumption I could put into place, maybe to get rid of some annoying edge case or something that's tripping me up, or something like that? Is there another assumption I could put into place to make this problem solvable in a sense? So this is an important, skill to have, being able to kind of read into the problem or read into the assignment and pull out the implicit assumptions. But that being said, being a math guy, I usually like when things are made quite explicit. But this is an example of where we have to pull out a couple of implicit assumptions. But we see that with a right triangle with 3 sides, they are related to one another through the Pythagorean theorem. X squared plus 8 squared equals 10 squared. Or I see that x squared plus 64 equals 100. And again, as we mentioned last time, we haven't gone over yet how to solve quadratic equations in general, but we know a pattern to solve linear equations where we isolate the variable term, and then we kind of isolate or figure out what the variable has to be. Can I isolate the variable term here following a similar pattern? Sure, I could do that. I might get stuck at the next step, but let's see where that brings us. And we see, okay, x squared equals 36. I know that 6 squared is 36. So x has to be 6. And I know that it's got to be in feet. I know that just kind of reasonably uh from the setting, but I also see that if 8 is in feet, I have square feet here. 10 is in feet, so I have square feet on the right side. I need to have x squared being square feet, so x has to be in feet, right? Or I could think this unit is in 36 square feet, so this has to be 30, or this has to be x squared square feet, which means x has to be 6 feet. One other note here is there's this idea of similar triangles. You might remember this from, say, geometry, that we have the famous 3, 4, 5 triangle, because 3 squared plus 4 squared equals 5 squared. But if we scale this triangle up, if we multiply all of the sides by some number, then we get an equivalent triangle. So the 3, 4, 5 triangle is equivalent to, say, if I multiplied everything by 3, I can have a 9, 12, 15 triangle. Or if I multiplied everything by 2, I'd have a 6, 8, 10 triangle. So I might have seen this 8 and 10 and said that feels like a 3, 4, 5 triangle multiplied by 2, right? The hypotenuse of 10, 5 times 2, and then 8 is 4 times 2. So I might have recognized right away that x should be 6 feet. So sorry, my dog is licking incessantly for some reason. um, just crazy day this morning, I suppose. Okay.
We see the dog.
Oh, well, actually, I have a picture of him on my phone. I'll show you on my phone. Here. I don't know if I can get the camera pointed at him. He's kind of laying on the floor in his bed, but he's, for some reason, licking the side of his bed constantly. I don't know if you can hear that or not. If you can't hear it, it's not a big deal. But um, okay, any questions on this? Yeah, his name is Bentley, and we rescued him. He came with that name. We rescued him about 10 years ago, so he's about 12 now, and he's starting to become a senior dog, and starting to, I think, get a little bit of dementia. So he's sometimes gets in these, like, whatever trances or whatever, where he just, like, incessantly licks things. um all right, so let's work on this problem. This is another geometry problem. So a rectangular basketball court, 20 feet wide, 42 feet long. Merrick wants to build a fence to surround the court. He wants the fence to be a rectangle, and he wants to be 5 feet from each side of the court. How many feet of fence will he need? So let's take maybe 3 minutes or so, work through this problem, and then we'll discuss it. Okay, so this one, we actually don't even really need to come up with a variable here. So we have a basketball court that's 20 feet wide, 42 feet long. So drawing a diagram, the green would be the court. We want to build a fence that's around the court. The fence should be a rectangle and 5 feet from each side of the court. So the blue rectangle represents the fence. And we notice that the width and length are both going to be 10 feet longer for the fence because 5 feet on each side. So the length of 42 feet becomes 52 and 20 turns into 30. And we can just find the perimeter directly. If we didn't know the length and width to start with, the perimeter would be, well, the length would be, the length of the fence would be 10 longer than the length of the court. And the width of the fence would be 10 longer than the width of the court. And we would double that, right? This is just our perimeter formula, 2 times L plus W. Right, we going from one corner to the other, we have to go across one length and one width, and then we double that to go around the other way. You could also think of it as 2L plus 2W, that you have to traverse the length twice, going one direction and the other, and same with the width. And then we could plug in L and W if we wanted to. This would give a more general form for an arbitrary court of a certain length and width. Any questions on that one? Okay, so let's move on to 3.5 then, solving uniform motion applications. And the main formula that we're going to use here, distance equals rate times time. And so rate we think of in this context as being basically speed. Okay, so let's look at this first question. A commercial jet and a private airplane. Oh, kind of as a side note, I know the book does this kind of whole like grid kind of thing. I actually find that a little more confusing. If you like writing out the grid, writing out all of the components in some kind of grid form, you can definitely do that. I actually find it seems to me to be an extraneous step. I find it a little more confusing to go that extra step and try to align everything in that grid, especially when you get to the more challenging problems. For the straightforward problems, it works pretty nicely, but I think with the challenging problems, it's almost kind of gets in the way, that step. But if you like that method, the way the book does it, certainly feel free to do that. Commercial jet and a private airplane fly from Denver to Phoenix. It takes the commercial jet 1.4 hours for the flight, takes the private airplane 2.1. The speed of the commercial jet is 185 miles per hour faster than the speed of the private airplane. Find the speed in miles per hour of both airplanes. Okay, so it doesn't really matter that it's going from Denver to Phoenix, but I think pretty much everything else is fairly essential information. It doesn't so much matter that it's specifically a commercial jet and a private airplane, but it is important to keep those in there because that's what distinguishes between the different speeds and the different times and so on. Okay, so these both fly from Denver to Phoenix from one place to another. It takes the commercial jet 1.4 hours. It takes the private airplane 2.1 hours for the same flight. And the commercial jet travels 185 miles per hour faster. So something that's, I suppose, a little bit interesting here is we're not actually told the distance between the two cities. We just know that it's the same distance. So that's an important note, is we don't know what the distance is, but they traveled the same distance. Okay, so distance equals rate times time. Well, the distance for the commercial airplane, I'll put a little subscript C to indicate that this is related to the commercial airplane, is the rate for the commercial airplane times the time for the commercial airplane, and similarly for the private plane. Distance for the private airplane equals rate for the private airplane times time for the private airplane. This is just applying this basic formula to each of the airplanes. So I feel like people were doing this for Taylor Swift when they were trying to figure out if she was going to make it from where Tokyo to Vegas or LA or something and then drive to Vegas. I don't know. So, okay, so we know that the distance the commercial airplane and the private airplane went were the same distance. We'll just call that D. The commercial airplane goes 185 miles an hour faster. Its speed is 185 miles an hour faster than the private airplane. So the rate or the speed for the commercial airplane is 185 more than the speed for the private airplane. So we've used this piece of information. And the time that it took the commercial jet was 1.4 hours. I want to be a little cognizant of my units here, but my speed is in miles per hour. My time is in hours, so hours and hours match up, right? If for some reason my speed was given in like, miles per minute or something, and I was given time in hours, I'd want to convert everything to be minutes or everything to be hours or something, but that doesn't apply here. Coming over here to the private plane, the distance for the private plane, again, they both went the same distance. We'll just call that D. The rate for the private plane, we don't know. But we do know, let me use this, we do know that the private plane took 2.1 hours. Okay, so I have two equations here. I have two equations. I have two unknowns, the distance traveled and the speed of the private plane. I also kind of hiding in the background have the speed of the commercial plane. That's another unknown, but we don't see that explicitly in these two equations. I have two equations. I have two unknowns. We've seen a couple of problems like this before. We had two equations with two unknowns, and we saw that, one approach was to try to solve one equation for one variable and plug in to the other equation, but another one was we can use the what's called the transitive property of equality, that if A equals B and also A equals C, then B has to equal C. Since we have the same distance equals this and this, it must be true that the right side of the left equation and the right side of the right equation are also equal. Because each of these two sides of this equation have to also equal D, the total distance traveled. Okay, so what can I do? I can multiply out. And if you don't like having the subscript floating around, you can just call this X or something like that. That doesn't really matter. I'm just keeping that little P subscript just to remind myself this is for the private plane, so I don't have to really refer back at the end or do any extra work. I want to figure out what is 1.4 times 185. I'll just come over really quickly to the calculator, do that multiplication. 1.4 times 185 gives me 259. And that's equal to 2.1 times the rate or the speed for the private plane. I want to isolate my variable term. I'll do that by subtracting 1.4 rate of the private plane from both sides. That cancels out on the left side. I get 259 equals 2.1 minus 1.4. I think that's 0.7 times the rate. And then I'll divide both sides by the coefficient of the variable to isolate the variable. So we're dividing by 0.7. And maybe I could do this division, but if I move the decimal point, I have 2,590 divided by 7. That's kind of annoying to do. Let me just do that on the calculator. Whoops. So just do 2,590 divided by 0.7 on the calculator. And that gives me 3,700. Oh, sorry. I was going to say that seemed a little fast. Well, so just as a little learning point, I did 2,590 over 0.7 because I had in my mind when I was saying do 2,590 over 7, but that's annoying. So just I still had stuck in my mind 2,590. This gave me 3,700. But given the context, does it make sense that a plane travels almost 4,000 miles an hour? Probably not. That doesn't seem right. That doesn't seem in line with, taking an hour to go from Denver to Phoenix. So I knew that something was wrong right away. And I just look over, I say, oh yeah, I put the extra zero in and kept the 0.7 because I just, wrote the number in wrong. So just as an aside, like I mentioned in these problems, you have a lot of context. You can use that context to help you out. So the rate of the private plane then is actually 370 when I get rid of the extra factor of 10 that I mistakenly inserted in there. And I know this should be miles per hour. I know it should be miles per hour because that's kind of what makes sense. And that's also what I have miles per hour here, miles per hour there, hours there. So, right, all of the units make sense from the original statement. I need to figure out the speed of both airplanes. So let me make sure that I fully answer the question. The commercial airplane, the commercial jet travels 185 miles an hour faster. So the speed for the commercial jet, 370 plus 185. And that gives me 555. And I guess at this point, I could say something like the speed of the private jet is 370 miles per hour, and the speed of the commercial jet is 555 miles per hour. So I think the real challenge of this problem is getting each of these equations set up. So recognizing that this is a problem that's going to use distance equals rate times time, that formula, and then seeing how to apply the formula. In this case, I had information that seemed kind of separate between the two planes. So I chose to set up two separate distance equals rate times time relationships, one for the private plane traveling this distance in 2.1 hours, one for the commercial jet traveling this distance in 1.4 hours. and then go from there. And after setting all of that up, I realized, oh, okay, I have the same distance in both of these. That's what I can use. That's kind of my common ground that I can use to relate those. If these were two different distances, if one was going from Denver to Phoenix and the other one was going from Pittsburgh to Cleveland, we wouldn't have enough information here to actually solve the problem. But since it's the same distance, that's the common thread that can tie these two together. And I realized that after kind of writing out the two equations. So a lot of times in an application problem like this, maybe you read the problem and you don't immediately see the entire strategy from start to finish. But can you see far enough to take a step or two steps? If you can, then sometimes after you take that step, you get an extra clue, and that gives you a little more information about the strategy you can use. And you go another step further and you get a little more, right? So sometimes it's not clear from the outset what the entire strategy for the problem is, but always ask yourself, is there something I can do to move myself forward? Even if it's as simple in a sense as just rewriting the important information, the pertinent information you're given. So just writing out these 4 pieces of information. Okay, so we'll take a few minutes to do this problem, the Kathy and Cheryl problem. And as always, if you want to work ahead, if you finish early, feel free to. But take about, say, 3 or 4 minutes to work through the Kathy and Cheryl problem, and then we'll discuss it. Okay, so this problem is pretty similar to the plane one. So we have two people, Kathy and Cheryl. They're both walking on a course. Again, we're inferring from the problem statement that they're both completing the same course, the same distance. Kathy completes the course in 3.6 hours. Cheryl completes it in 6 hours. And Kathy walks 2 miles per hour faster than Cheryl. So if we start with our information about Kathy and about Cheryl, we see that, again, we're given the information kind of separately. So we'll start with two separate distance equals rate times time formulas. The distance for the course equals Kathy's rate, her speed, times 3.6 hours that it took her to complete it. And for Cheryl, her distance, the distance for the course equals Cheryl's speed, the rate for Cheryl, times 6 hours. And now we see two things. We have a relationship between Kathy's and Cheryl's speeds, their rates. Kathy walks 2 miles per hour faster than Cheryl, so the rate for Kathy is the rate for Cheryl plus 2. And we also note that these two equations are tied together by this common distance, the fact that they both completed the same course, which we're inferring. They completed the same course, so they went the same distance in these times. So I know that the rate for Kathy times 3.6, or in other words, the rate for Cheryl plus 2 times 3.6 is equal to 6 times the rate for Cheryl. I can distribute on the left. I can isolate my variable term. And then isolate my variable. And 7.2 over 2.4, well, that's 72 over 24. I think that's just 3. And this should be miles per hour for the rate for Cheryl. The rate for Kathy is 2 miles an hour faster than that, so the rate for Kathy 5 miles per hour. So I think pretty similar to our plane problem that we did. Maybe the numbers are a little more manageable in this one. Any questions on either of these? Let me make all of the text the same color here. Okay, so next question or next example. Sisters Helen and Ann live 472 miles apart. For Thanksgiving, they met at their other sister's house partway between their homes. Note that it says partway, not halfway, so we don't know how close the sister's house is to Helen's or Ann's. Helen drove 3.4 hours, Ann drove 3.6 hours. Helen's average speed was 5 miles an hour faster than Ann's. Find Helen's average speed and Ann's average speed, both in miles per hour. So let's draw a diagram. Here we have Helen's house. And here we have Ann's house. And somewhere in between is the other sister's house. We know this distance is 472 miles. Helen to Ann is 472 miles, so that's this piece of information. Helen drove 3.4 hours. Anne drove 3.6 hours. And Helen's speed was average speed, was 5 miles per hour faster than Anne's. So the speed for Helen is the speed for Anne plus 5. Okay, so in this case, it's unlikely that Helen and Anne drove the same distance. But I still do have separate information for Helen and Anne. Let me still write out my two separate distance equals rate times time formulas. So for Helen, well, this distance, maybe I'll make it green. We'll call this the distance that Helen traveled, and we'll call this the distance that Anne traveled. So for Helen, distance equals rate times time for her. The distance for Helen equals rate, Helen's speed. The rate for Helen times the time that Helen drove, which was 3.4 hours. For Anne, Anne's distance traveled is her rate times the time that she traveled, 3.6 hours. Now I know that I can say that, well, Helen's speed was Anne's speed plus 5, so I can make that simplification here and get rid of one variable anyway. But now I have a bit of an issue because the distance for Helen probably isn't the same as the distance for Anne. So I have kind of three variables and two equations. I'm not going to be able to link any of these up really easily, but I do note that there's one more piece of information in my problem statement that I haven't used yet, specifically that Helen and Anne live 472 miles apart and their sister lives between them. Well, I might notice from the diagram that Helen traveled a certain distance and Anne traveled a certain distance. The sum of those two distances has to be that total distance. So for instance, I don't know that Helen's distance and Anne's distance was the same, like I did with the plane problem or the walking problem. But I do know something about how they relate to one another. Their sum has to be a certain number. In other words, I know that Helen's distance plus Anne's distance has to be 472. Or in other words, I have this relationship. So what would I do here? I would multiply everything out, combine like terms, isolate the variable term, isolate the variable, just like always. 3.4 times Anne's speed, the rate for Anne, plus 5 times 3.4 is what? So that would be 1/2 of 10 times 3.4. 1/2 of 34 is 17. Plus 3.6 times the rate for Anne times Anne's speed, her average speed, equals 472. I have like terms that I can combine. So 3 plus 3 is 6, and then the 0.6 plus 0.4 gives me one more, so 7 times and speed plus 17 equals 472. And now I'm down to a more straightforward linear equation. I can isolate the variable term. (472 minus 17), so it's that 452 plus 3, 455. And since I'm feeling lazy, we'll just put this in the calculator. So this gives me 65 miles per hour. So Anne's average speed was 65 miles per hour. Helen's average speed was 5 faster than that. So 70 miles per hour. And we could write it in a sentence. Anne's average speed was 65 miles per hour, and Helen's average speed was 70 miles per hour. As kind of a side note, and this applies to this problem as well as both of the previous ones, we never actually said what the distance was. We didn't actually say how far either of them traveled or what the distance between Denver and Phoenix is or whatever. So we never actually found these distances. We just found the rates. That was what we were told to find. If we were curious, we actually could go back. Now that we have, say, Helen's rate, we could go up here and find how far did Helen travel. We have Anne's rate. We could go back here and find how far did Anne travel, just by plugging in those rates for Helen and Anne. Or we could do the same thing for the planes up here, as we could figure out, according to this problem, how far apart are Denver and Phoenix. Or the same thing actually over here with the two people walking the course. We never figured out what distance the course was, but now that we know each of their rates, we can come back up here and plug into either one of these equations to find the distance for the course. So just because we're not finding the distances doesn't mean we can't. We could still find the distances. We could figure out everything about the problem if we wanted to. It's just not part of the problem statement, so we're not worried about it. But if we were interested, we could go back and find the distances now that we have the rates. Okay, so take a look at this problem, this Julian rides his bike problem. Read through it carefully. Try to figure out what the distance equals rate times time, pieces are, I suppose. Note that he rides his bike uphill and then turns around and rides downhill. So it's almost like he has two separate trips that are the same distance. So he's going to ride uphill a certain distance, turn around and ride downhill a certain distance. So maybe if you think of it as two separate trips going the same distance, that's a little bit of a hint as to where to maybe start this problem. This one's a little bit more challenging than the last one that on the worksheet. So let's take maybe 3 or 4 minutes, work through this one, and then we'll touch base in 3 or 4 minutes. Okay, let's work through the answer to this one. So we have a hill. Let's maybe draw a diagram of the hill. So Julian rides his bike uphill. So here he is on his bike. He goes uphill a certain distance for 45 minutes, then turns around and rides back downhill the same distance, going uphill 45 minutes and downhill 15 minutes. His uphill speed is 3.6 miles per hour slower. So let's say rate uphill is 3.6 miles per hour slower than his downhill speed. So that's rate downhill minus 3.6. And this is in miles per hour. Find his uphill and downhill speed in miles per hour. Here we got to be a little bit careful. It might be tempting to just jump into our equations, distance equals rate times time, but we have our speeds in terms of hours and miles per hour, but our times in terms of minutes. Let me come over here and say, well, 45 minutes is really 0.75 hours, and 15 minutes is 0.25 hours. Or we could say 3/4 and 1/4, whatever way you prefer. So that's the first thing that we have to really be careful about here, is making sure all the units match up. And now the units match up. He biked uphill for 3/4 of an hour, downhill for 1/4 of an hour, for a total of 1 hour of biking. Okay, so for the uphill portion, his distance uphill, which what is called D, it's going to be the same as the distance downhill because he returns back to where he started. So we'll just call that D. It's the rate uphill times the time uphill, and importantly, time uphill in hours, 0.75 hours. And then downhill, same distance. The distance downhill is the same as the distance uphill. Rate downhill times time that it took him to go downhill, 0.25 hours. And I see this similar setup here. I can substitute in the rate uphill as rate downhill minus 3.6. And I can use this common distance, uphill versus downhill being the same distance, to connect my two equations. Rate uphill is just rate downhill minus 3.6. And that's equal to rate downhill times 0.25. Maybe if we multiply both sides by 4, that might make things a little easier. Because really, this is kind of like 1/4 and 3/4, right? Four times 0.75 is 3. And 4 times 0.25 is just 1. Or that entire right side just simplifies to just rate downhill. On my left side, distributing, so 3 times 3 is 9, 3 times 6 is 18 with a decimal point, so I think this is 10.8. I can isolate my variable term. Isolate my variable. So I have negative over negative is a positive. 10.8 over 2 is 5.4. And that's miles per hour. So his rate downhill, 5.4 miles per hour. And then his rate uphill is 3.6 lower than that. So if we do 5.4 minus 3.6, so that's 1.8. Miles per hour for the rate uphill. Now, kind of as a side note, on this problem, if you had kept these as 45 and 15, the formulas here, since we're equating them with respect to the distance traveled, it would have still worked out. You still would have got the right answer. So why is that? Well, this 45 minutes was like, what do? We took 45 minutes divided by 60 minutes per hour, and that's what gave us the 0.75 hours. But we would basically just be dividing both sides by 60 on this equation. So just kind of coincidentally, because of the setup of this problem, if we made a mistake and kept it at 45 and 15 minutes and just made these instead of 0.75 and 0.25, if we made them 45 and 15, we still would have gotten the right answer. So why should I switch everything into the same units? Well, if we had a problem like this one, where the sisters were driving toward each other and they had a total distance of 472 miles. Well, now if we don't, if we had been given this information in different units, if we don't move everything to the same unit, instead of these being connected to each other with an equals, so that kind of common factor more or less just divides out, they're connected to each other with a plus now, and they're equaling something that is a different unit. We're not going to get the right answer in a situation like this if we don't put things in the right units. So it's always good practice to put everything in the right units. Just letting you know that, just in case you had gone through this problem with the 45 and 15 and you say to yourself, wait, well, you said that wasn't the right approach, but I got the same answer you did. And that's true. It would happen to work out in this case, but we want to establish habits and ways of doing things that are going to work in general. So in this specific case, fixing the units, fixing units or not would have got us the same answer. But in the general case and other problems, failing to adjust the units would be a lot more problematic. Okay, so last two problems, last lecture problem, and the last worksheet problem. Lizette is training for a marathon. At 7 o'clock, she left her house and ran till 8:45. Then she walked until 11:45. She covered a total distance of 20 miles. And her running speed was 6 miles per hour faster than her walking speed. Find running and walking speeds in miles per hour. So we want the answer in miles per hour. We should probably think of these times in terms of hours. Okay, so she left her house at 7 and ran until 8:45. So running (7 o'clock to 8:45) is 1.75 hours. Right. I want to figure out how many hours elapsed from 7 o'clock to 8:45. 1 3/4 hours, 1.75 hours. Her rate while running, let's call it, should we call it R sub R? I guess so. R sub R. We don't know what it is, but we do know that her rate or her speed while running was 6 miles per hour faster than her speed while walking. And she went some distance while running, but we're not sure what distance. So her distance while running is going to be her rate while running times the time that she was running, 1.75 hours. And that's our first of the two equations. For walking, she walked from 8:45 to 11:45. In other words, 3 hours. We don't know her rate while walking. And we also don't know her distance while walking. But we do know that her distance while walking is the rate while walking times the number of hours that she walked. So I can swap in the rate while running as rate while walking plus 6. So that's going to get me a little closer to my goal. But I still have these two different distances now, distance while running and distance while walking. Is there a piece of information I haven't used yet? She left at 7, ran until 8:45. She walked until 11:45. The speeds. I haven't used the total distance of 20 miles. And that's how I'm going to connect these. Distance while running plus distance while walking equals 20 miles. So here, if I had, come up here and said, 105 minutes and 180 minutes, like I mentioned in the previous problem we did, that wouldn't have really caused the problem as far as getting the correct answer at the end. But in this problem, it would cause a problem. So we have to make sure that our units are appropriate. Because here we have 20 miles on the right. Okay, so the distance while running is, well, I'm going to swap rate while running as rate while walking plus 6. Times 1.75 hours. Well, it's not equals, plus. The distance while walking is 3 times the rate while walking equals 20. And we've made our way down to a linear equation in one variable, and we'll solve for the rate while walking. Let's multiply out and combine like terms. 6 times 1.75, well, that's 6 plus, 3/4 times 6 is what? Well, let's just do 6 times 1.75. I'm not My brain isn't working too great today, so I'm going to try to avoid mental arithmetic if I can. 10.5. So 1.75 rate while walking plus 10.5 plus 3 rate while walking equals 20. I'll combine like terms. 4.75 rate while walking plus 10.5 equals 20. And I'll isolate my variable term. So 9.5 equals 4.75 rate while walking. And then I'll isolate my variable. I think that should be 2. Yep. Rate while walking is 2 miles per hour. Does that seem reasonable? Yeah, that seems pretty reasonable. I know I shouldn't get, say, a negative number. I know I shouldn't, within reason have like 20 miles per hour or something, or else somebody made a kind of a crazy problem. But we see the rate while walking is 2 miles per hour. And then coming back up here, the rate while running 6 miles an hour faster than that. Rate while running is 8 miles per hour. Any questions on that? Okay, so maybe take about 4 minutes, work through this problem, and then we'll come back and discuss it. Okay, so let's work through this one. So we have a marsh, like a pond or something that has a perimeter of 9 miles. Robert walks around it one direction, Sasha the other direction. They meet somewhere along the way on the other side, and Robert walks twice as fast as Sasha. If they meet after 1.5 hours, how fast does Robert walk? So we can draw a diagram like this on the left over here. But we see that kind of simplifying this or just making a more diagrammatic um, graph over here, we see that in some sense, the distance between Robert and Sasha when they start is 9 miles going the long way around the pond. That's the distance that Robert walks plus distance that Sasha walks. So this has the feeling of like the two sisters meeting in the middle kind of thing. Robert walks one direction, Sasha walks the other direction, and they meet somewhere in the middle, but not halfway. So what's Robert's speed? Well, we know that Robert's speed is twice that of Sasha's. And for Robert, we can say that Robert's distance traveled is his rate times 1.5. His rate times 1.5 hours that he walked for. And the same is true for Sasha. Distance Sasha traveled is Sasha's rate times 1.5 hours. But Robert's rate is twice Sasha's rate. So we'll just replace rate for Robert by twice rate for Sasha. And again, we don't have a direct link between these two equations, but we do have one piece of information we haven't used, and that's the total distance of 9 miles. We know the sum of their distances has to be 9 miles. And continuing on from here, we see that 2 times Sasha's rate, Sasha's speed, times 1.5 plus 1.5 times Sasha's speed equals 9. Or this is 3 times Sasha's speed plus 1.5 times Sasha's speed. If we combine all of those like terms, that gives me 4.5 times Sasha's speed is 9 miles. And then if I divide both sides by 4.5 to isolate the variable, I see that Sasha's speed is 2 miles per hour. And what do I want? I really want Robert's speed. Robert's speed is twice that. So this would be the answer to this problem. Robert's speed is 4 miles per hour. Are there any questions on any of these uniform motion applications or these distance equals rate times time applications?
Are these going to be on our first exam?
Yeah, I think the first exam goes through, is it chapter, it's either chapter 3 or chapter 4. Let me bring up my course schedule really quick here. I had trouble getting Adobe to close down, so I'm hoping that it won't give me trouble starting up. Okay, it started up just fine. Yeah. Everything has a pop-up attached to it now. Yeah, so if we look at the schedule, Unit 1 exam is on chapters 1 through 4. So that covers this and also our next topic, applications with linear inequalities, and some of our basic material and graphs. Yeah. And that Unit 1 exam will be the week of March 7th. So just, keep an eye out for, oh yeah, just keep an eye out for the the material related to that exam. As a side note for the exam, the Examity practice exam is posted. So I do recommend strongly that folks log on, get set up on Examity and all of that well in advance of that Unit 1 exam week. So that's open now. You can go and knock that out pretty quickly. And again, the purpose of that Examity practice exam, like I said in the announcement, was it's not, it doesn't count toward your course grade or anything like that. It's really just to get you set up on Examity and go through the process once in a low stakes situation, so that when you're doing the actual Unit 1 exam, you've gone through the Examity process once, you know how it works, you made sure that all of the tech on your computer and internet and all of that works well. So definitely, do that well in advance of the Unit 1 exam week, and then Unit 1 exam should go pretty smoothly. So any other questions? All right, then